All of the reactions we've looked at so far have been at 25 degrees Celsius and 1 mole per liter. If there happened to be a gas, it's 1 atmosphere, etc., etc. But what happens if you're not at 25 degrees Celsius? What if you're in Alaska or you're in Death Valley or something, someplace that's really hot? That would be when you have a temperature change. But also, what would happen if you're not at 1 mole per liter? Maybe you're at 0.01 mole per liter, or you have 10 mole per liter, these kind of things. So for all of these kind of conditions, you need what's called the Nernst equation. The Nernst equation is E equals E naught minus RT over NF, natural log of Q. Okay, so Nernst equation is doable. It's a little tedious, but it is absolutely doable. And if you're going to use the Nernst equation, what you want to do is first of all think about what the constants are. R is what I called the energy gas R, 8.3145 joules per Kelvin per mole. Temperature is in Kelvin, big surprise there. F is the Faraday constant, 96,485 coulombs per mole electrons. N is the moles of electrons transferred. Q is our good friend, the reaction quotient from the equilibrium chapter. Q looks just like K. It's products over reactants. And this is where you can use like 0.01 moles per liter instead of 1 mole per liter, stuff like that. But also E naught is the standard E potential, the standard cell potential. So in this Nernst equation, you want to first find the cell potential under standard conditions, i.e. if you're at 25 degrees Celsius, 1 atmosphere, 1 mole per liter, all that stuff. And then you plug in the minus RT over NF natural log of Q part to find the non-standard cell potentials. And if you put all that together, that's going to give you E, which is the cell potential under the non-standard conditions.
A zinc-copper cell shows a potential equal to the standard potential of 1.10 volts when both zinc and copper are in solution at the same concentration. If more copper ion is added to the cathode compartment solution, however, the cell potential increases.
In this reaction, we have the copper 2 plus and zinc making zinc 2 plus and copper. We saw earlier that the cell potential is about 1.10 volts if you are at 25 degrees Celsius, concentrations 1.0 moles per liter, etc., etc. However, what they did in this reaction is they added a whole bunch of copper 2 plus. Now, if you think about Le Chatelier's principle, adding a lot of copper 2 plus, a reactant, is going to make this reaction move more to the products. So cell potential, which is actually a measure of how much reactant is going to product on one level, becomes more positive. If you look in the video, it's 1.11 volts now instead of 1.10 volts. So Le Chatelier's principle predicts the reaction will move to the right, and that's what we see in the cell potential. The cell potential will become more positive if you have a shift to the right. It will become more negative if you have a shift to the left. So it's kind of cool how Le Chatelier's principle will still help us out here, but we can use the Nernst equation to actually calculate numbers like the 1.11 volts. Now, cell potentials under the Nernst equation are usually small differences, so you won't see huge gaping changes in the cell potential, but sometimes those small potential changes can be enough to really make a difference, so it's worth going through an example to see how this works. So let's do an example. We want to find the cell potential E when the zinc 2 plus concentration is 0.0010 moles per liter, the pressure of the hydrogen gas 0.10 atmospheres, the pH is 0, and the temperature is 290 Kelvin. Okay, so first of all, let's look at those numbers just for a bit. The zinc 2 plus is certainly not 1 mole per liter. It's 0.0010 moles per liter. So this is a non-standard condition. Also, the pressure of the hydrogen gas would be 1 atmosphere if it was standard. We have 0.1 atmospheres. Now, we're going to see in a little bit that pH of 0 does mean 1 mole per liter for acid, so that's standard. But standard temperature is 298 Kelvin, and we're at 290 Kelvin. So we have a lot of values here which are not standard conditions. And so this is why we need to use the Nernst equation. So if you look up on tables, you'll find zinc going to zinc 2 plus and H plus going to hydrogen gas, and there's the two cell potentials right there. The second reaction is the She reaction. It's kind of the way that all the cell potentials are measured. But the important thing is that when you add those reactions together, the electrons cancel out. You've got 2H plus and zinc going to zinc 2 plus and hydrogen gas, and the cell potential positive 0.76 volts. So positive values are the ones that are going to occur. This is a spontaneous reaction, and if everything was at 1 mole per liter, 1 atmosphere of gas, and temperature was 298, we would expect positive 0.76 volts. But 3 of those 4 concentrations there are not going to be standard. We don't have standard zinc 2 plus, we don't have standard H2, and the temperature is weird. So we have to accommodate for that in the Nernst equation. But before we leave this page, notice how 2 electrons canceled when we added the cell potentials together. That means N is going to be 2. 2 moles of electrons are transferred in this reaction. So the Nernst equation, E equals E naught minus RT over NF natural log of Q. Okay, well, the standard cell potential, E naught, is 0.76 volts. So again, if everything was standard, that's what we'd see. Then it's minus RT over NF. R is 8.3145. The Kelvin temperature, 290 Kelvin. The N, moles of electron transferred, we saw on the earlier page, was 2. And F, the Faraday constant, 96,485. Now, all of that is times the natural log of Q. Q is the reaction quotient, which is like an equilibrium constant. It's going to be products over reactants. So if you look at the reaction we're seeing here, you don't include solids and liquids, but we should put in something for zinc 2 plus, for hydrogen gas, and for the H plus concentration. H plus is 10 to the power of minus pH, if you remember from the acid-base reaction. 10 to the minus 0, which is what our pH is just 1 mole per liter. So we can essentially ignore the H plus for this one because it's 1 mole per liter. So Q is products over reactants. That's going to be the zinc 2 plus times the hydrogen gas, the pressure of the hydrogen gas, divided by H plus squared. The zinc 2 plus is 0.001. The pressure of the hydrogen gas is 0.10 atmospheres. We'll divide by 1.0 squared. So again, kind of tedious, but all stuff you can do. That's what you would do to calculate Q. Then when you plug this all together, the standard cell potential, 0.76 volts, all the minus RT over NF natural log of Q stuff gives you positive 0.12 volts. So when you add those two together, you get positive 0.88 volts. That's the cell potential under these non-standard conditions. So in this case, it becomes more positive. Wow. So if you think about this long enough, the zinc 2 plus and the H2, the products, have less than the desired ideal amounts. On the reactant side, H plus and zinc, they're fine. They have the standard amounts. So if the product side is less, that's kind of like saying by Le Chatelier's principle, like you're taking away a product. And if you take away a product by Le Chatelier's principle, the reactants will move to the product side. And as we said earlier, reactants moving to product side makes the cell potential more positive. So that's one way to justify why the cell potential goes up under these non-standard conditions. It's kind of cool how Le Chatelier's principle helps us out. Nernst equation is tedious, but totally stuff you can do. And if you follow these steps, you should be good as well.